Hello, and welcome to this online lecture. My name is Patty Kokish, and I teach math in the Northwest region at Ivy Tech. Today we are going to be covering topics from week 13 of your online Math 136 class. We are going to start with, hold on one second, this doesn't appear to be working. We are going to be starting with new material from Chapter 6. We're going to do 2 sections, and then I'm going to go back and review a few different problems from the earlier parts of Chapter 6, since you do have a Chapter 6 quiz to do this week. So we're going to start with a new section, which is Section 6.7, Financial Models. So the first thing that we want to do in this section is to be able to determine the future value of a lump sum of money. So we have a theorem here. This is a simple interest formula. So if a principal of P dollars is borrowed for a period of T years at a per annual interest rate of R, which is always going to be expressed as a decimal, then you can find the interest by taking the principal times the rate times the time. So I equals PRT. So please make sure you keep in mind that P is your principal, T is time in years, and R is your interest rate, but written as a decimal. And this gives you simple interest. So we have a couple of kind of terms to go over. First of all is that annually means it's going to be once a year. Semi-annually means twice a year. Quarterly is going to happen every 3 months, so that's 4 times a year. Monthly is 12 times a year since there are 12 months, and daily is going to be 365 times per year. So if we want to compute compound interest, we can use a little bit of what we just learned along with our simple interest formula. So let's say a credit union pays an interest of 4% annually, which is compounded quarterly on a certain savings plan. If $2,000 is deposited in such a plan and the interest is left to accumulate, how much is in the account after 1 year? So we're not just talking about simple interest in this case, we're talking about something that's compounded quarterly. So what we need to do is we need to figure out what will our interest be after the very first quarter. So if we'd like to do that, what we do is we take our 2,000, which is our principal, multiply it by our rate, which is 0.04, and multiply it by our time in years. In this case, we're just talking about the very first quarter. So that's going to be 3 months, which is 1/4 of a year. So we multiply by 1/4. And if you do all of that, you should get $20. Now that gives you the interest. What we would like to find now is the new principal. So if you think about it, if you deposit money into an account, you have whatever you deposited plus whatever interest you make. So in order to figure out the new principal after the first quarter, you take your $2,000 and you add your $20 to it, and you get $2,020. Now, if we want the interest after the second quarter, we basically do the exact same thing, except we use our new amount as our principal. So we know that after the first quarter, we have $2,020 in our account, so we use that as our new principal. And then again, we multiply by our rate, which is written as a decimal, 0.04, and our time, which we're just talking about the second quarter. So again, it's a 3-month period, which is going to be 1/4. So if you multiply all those, you get $20.20. That means we earned a little bit more interest the second quarter than the first quarter, which would make sense because we have a little bit higher of a principal. If we want our new principal, we take our old principal, which was $2,020, and add our interest, which is going to be $20.20. So you get $2,040.20 as your new principal after the second quarter. We're going to do the same thing 2 more times until we have the whole year. So interest after the third quarter is going to be our $2,040.20, which is our new principal, our rate, which is 0.04, and our time, which again is 1/4 of a year or 3 months. And you get $20.40. So again, we earned a little bit extra interest. In order to get our new principal, we take our $2,040.20, which was what was left after the second quarter, and add our interest from the third quarter. And we get $2,060.60. And then interest after the fourth quarter, we're going to take our new amount, which is $2,060.60, multiply by our rate, which is 0.04, and our time, which again is 3 months or 1/4 of a year. And we get $20.61. So our new principal after the entire year is going to be our $2,060.60, and we need to add our interest to that, our $20.61. So we end up with $2,081.21 as our new principal after 1 year. Now, what we can do is we can kind of develop a little formula here. We know that interest is going to be principal times rate times time. Time is going to be 1 over n, okay, if we're talking about compounding different amounts of time. And so what we have here is principal times r over n. So what we can do is we can kind of develop a formula here. If we take our principal and add our principal times our rate over our number of times compounded in a year, then what we can do is develop a formula for our amount. So what we know is that our amount is going to be our principal times 1 plus r over n. So after 2 compounding periods, if you're compounding it twice, you're going to do that twice, and you get p times 1 plus r over n squared. If you're talking about 3 compounding periods, you're going to do it 3 times this time, so you end up with p times 1 plus r over n to the third. And what we can say is because t years are going to contain n times t compounding periods, then we can use the following formula here. A, which is our future value or our future amount, is equal to our principal times 1 plus r over n raised to the n times t power, where n is the number of times in a year that it's compounded, t is your number of years, p is your principal, r is your rate written as a decimal, and a is your future amount. So we have this in a theorem right here. This is our compound interest formula. We basically just walked through some of the steps in order to generate this formula, but this is something that you can just memorize as it is. Again, T is in years, P is principal, annual interest rate is R, but written as a decimal. N is the number of times that it's compounded in a year, and A is the future value or future amount. So if we want to compare some different investments using different compounding periods, let's walk through this example here. Let's say we're going to invest $1,000 at an annual rate of 10%. We're going to do it compounded annually, semi-annually, quarterly, monthly, and daily. And we're going to see what the different amounts are. So if you're compounding annually, that means you're compounding once a year. So N is going to equal 1. So what we're going to do is we're going to use our formula, A equals P times 1 plus R over N to the NT. Now in this case, since it's just compounded annually, you can use this simplified formula right here, okay? But if you just let N equals 1, you're going to get the exact same thing. So we have 1,000 times the quantity 1 plus 0.1. Again, we write our rate as a decimal. And if we do that, we get $1,100. So that's our future value. So meaning if you take $1,000, put it in an account that earns 10%, and it's just compounded annually, at the end of the year, if you check your balance, if you haven't made any additional deposits, you will have $1,100 in there. Now, if it's semi-annually compounding, that means twice a year, N is going to equal 2. So in this case, we have a slightly different formula than we used for the first one. This one actually uses the R over N to the N times T power. So we have A equals our principal, which is 1,000, times 1 plus our rate, which is 0.1 divided by 2. 0.1 divided by 2 gives us 0.05. And then we raise that to the N times T power. N is 2 because it's semi-annually, and T is just 1 because we're just talking about 1 year. So 2 times 1 is just 2. So in your calculator, you can plug it in very carefully. All at once is fine if you put parentheses where you need to. If you want to do it step by step, though, you have to follow order of operations. So make sure you do the 1 plus 0.05 first, and then square that number, and then multiply by 1,000. And if you do that, you'll get $1,102.50. So a little bit more than the annually compounding, which makes sense. Basically, that means after a half a year, they recalculate your balance, and then you accrue interest on that whole new balance. So as things are compounded more and more frequently, you're going to make more and more money. So with quarterly compounding, we should expect it to be kind of close to the semi-annual, but a little bit higher. So since it's quarterly, that's going to be 4 times a year. So when we plug it in, we have our principal times 1 plus R divided by 4 to the 4th power, because it's just 4 times 1. That's N times T. So we have 1,000, which is our principal, multiplied by 1 plus, we know that our rate is 10%, So we would take 0.1 and divide it by 4, and we would get 0.025, and we raise that to the 4th power. Again, you can plug this all in your calculator at once, but if you want to do it step by step, you're going to add the 1 plus the 0.025 first, then raise it to the 4th power, and then multiply by 1,000. And if you do this, you get $1,103.81, which is right in the same ballpark as these other numbers, but again, it's a little bit higher, just as we would expect. Okay, for monthly compounding, that's 12 times a year. It's going to be every month. So again, we plug it into our formula. So we have 1,000 times 1 plus, and then if you take 0.1 divided by 12, you're going to get this number here, 0.00833. And then you raise that to the 12th power, and then you get $1,104.71. So looks like about 90 cents more than the quarterly compounding. And then daily compounding, that's going to be 365 times a year. So you take your 1,000 and you multiply that by 1 plus 0.1 divided by 365, which is going to give you 0.000274. And then you raise that to the 365th power, and you get $1,105.16. So you might notice that the annually compounding and the daily compounding are actually pretty close, $1,100 exactly versus $1,105.16. But as you look at these over a period of a longer number of years, maybe like 10 or 20 or 30 years, and you get into higher and higher balances, you will notice that these amounts, or the differences between annually compounding, daily compounding, become a little bit more significant. We also have something called continuously compounding. So the amount A after T years, due to a principal P being invested at an interest rate of R, so those are all our same variables, is going to be given by this. A equals P times E to the RT. Now E is just a button that you'll have in your calculator. It's just like pi, it's an irrational number. And it helps us figure out how to find our amount A if we have something that's continuously compounding. So that means even more frequent than daily. It's always happening. So we want to find the amount A that results from investing a principal of $2,000 at an annual rate of 8%, where you have continuously compounding for 1 year. So we're going to use this formula down here because we have continuously compounded. So we just plug our numbers in. We have 2,000, that's our principal. Our rate is 0.08. Never forget to write that as a decimal. And then we have times 1 because we just have 1 year. So in your calculator, again, you can plug this in all at once into your calculator, but make sure you're really careful. If you want to do it in stages, make sure you do your e to the 0.08 times 1 power first, and then multiply that answer by 2,000. And if you do that, you should get $2,166.57. Always ask yourself if your answers make sense. If you had gotten an answer of 21,000, you should probably think to yourself, it doesn't really seem reasonable that a $2,000 investment would yield $20,000 at the end of a year. We can also calculate effective rates of return. So let's suppose that you have $1,000 and a bank offers to pay you 3% annual interest on a savings account with interest compounded monthly. So in 1 year, we know that we would take 1,000 times 1 plus our interest rate, which is 0.03. We would divide that by 12 since we have compounded monthly, and we'd raise that to the 12 times 1 power, which is just 12. And so with that, we'd get $1,030.42. So if you think about it, if you invested 1,000 and after a year you have $1,030.42, the interest earned is at $30.42. So you just take whatever the future value is, or future amount A, and you subtract your principal P. So in this case, we earned $30.42. Now what we can do is we can use I equals PRT to kind of transform it back into a simple interest rate. So we know that T equals 1 because we just have a time of 1 year. I is going to be our interest that we earned. That's the $30.42. And in this case, P is our principal, which is our $1,000. So if we plug that in, so we would have $30.42 equals 1,000 times R times 1. And then we go ahead and multiply and divide in order to solve for R. We would get R equals 0.03042. which if we want to write it as a percentage would be 3.042%. So what this interest rate is called is the effective interest rate. So the effective interest rate is the equivalent annual simple interest rate that would yield the same amount as compounding after 1 year. And essentially what it allows us to do is to fairly compare various types of investments. So we do have a couple of formulas here. So the effective rate of interest, which can be denoted with R sub E, of an investment earning an annual interest rate of R is given by the following. So if we have compounding n times per year, then what you do is you take 1 plus your rate divided by the number of times that it's compounded and raise it to the n power, and then subtract 1. If you have continuously compounding, then you do e to the r power and subtract 1. So this is a good example of why effective interest rates are useful. It helps us calculate the best deal if we have different kind of offers on the table. So let's suppose you want to open a money market account. You visit 3 different banks and determine their money market rates. Bank A offers you 4% annual interest compounded daily. Bank B offers you 4.1% compounded monthly. And Bank C offers 3.95% compounded continuously. And we want to determine which one's the best. Now, the reason that we can't really tell which one's the best is because the daily interest rate is a little bit lower than our monthly interest rate. We know that daily interest rates are amounts after a certain amount of time, if we have daily, is going to be higher than monthly, but we have a little bit lower of an interest rate. And then the lowest interest rate of all is compounded continuously. Compounded continuously is the best, but the interest rate is different. So we can't really compare these without doing some calculations. So what we want to do is go ahead and use our formula. So we take RE, that's going to give us our effective interest rate. So we take 1 plus 0.04, which is our annual interest rate, written as a decimal for Bank A, so 0.04, divided by 365 because we have compounded daily, so n is 365. And then we raise that to the 365th power, and then we subtract 1. And if we do this, we get 0.0408084, which, if we want to change it to a percentage so it's a little easier to see, is going to be about 4.081%. Now for Bank B, we're going to do the exact same thing, except we have compounded monthly, which is going to be n equals 12, and then our interest rate's a little higher, 4.1%. So we do 1 plus our 0.041, divide by 12, raise it to the 12th power, and then subtract 1. And we get 0.0417793, which is going to be 4.178%. So out of Bank A and Bank B is the best so far because it's higher. We want to be earning as much interest as we possibly can. And then Bank C, we use our other formula here where we have E raised to the rate minus 1. This one's probably the easiest to plug in your calculator. So we do E to the 0.0395 power and then subtract 1. And if we do that, we get 0.0402905, which is going to be 4.029%. So Bank B is still the best, Bank A is second best, and Bank C is the worst. Okay, we can also determine the present value of a lump sum of money. So we have some present value formulas here. Present value P of $A to be received after T years, assuming an annual interest rate of R, which is compounded n times per year, is going to be given by this formula here. P, your present value, is going to be equal to A times the quantity 1 plus R over n to the negative nt power. Now, if we have interest that's compounded continuously, then we're going to use this formula down here where we have P equals A times E to the negative RT. So you'll notice these look very similar to our other formulas, except the A and the P are pretty much flip-flopped, and our powers are now negative. Okay, so a zero coupon or non-interest-bearing bond can be redeemed in 10 years for $1,000. So we want to know how much should you be willing to pay for it now. If you want a return of A, 7% compounded monthly, and B, 6% compounded continuously. So you'll see we have these two formulas written below their respective questions. This one is used for compounded continuously. It has the E in it. And this one we're going to use for compounded monthly. It has our N in it. So for A, what we're going to do is we're going to say P equals, that's going to be our present value, is going to be equal to our future value, which is 1,000, times 1 plus our rate, which is 0.07, divided by 12 because we have compounded monthly, and then that's raised to the negative 12, which is n, times t power, which is 10 years. So that would be the negative 120th power. So you can plug this into your calculator very carefully all at once, or if you want to do it in steps, you can do the 1 plus 0.07 divided by 12, and then raise that to the negative 120th power, and then multiply by 1,000. And you should get $497.60. Now for part B, all we have to do is take 1,000, which is our future amount, multiply by E, raised to the negative 0.06 because we have 6% compounded, times 10 power because we have 10 years, and we get $548.81. Okay. Fourth objective is to determine the rate of interest or time required to double a lump sum of money. So for example, we want to know what annual interest rate compounded quarterly should you seek if you want to double your investment in 6 years. So we know we're going to be using our compound interest formula. It doesn't really matter what our principal is going to be. It's going to take as long to double it if you're going from $100 to $200. Or if you're going from $10,000 to $20,000, it's going to be the same amount of time. So what we do is we know that our future amount, our A, we want that to be 2 times our principal. So that's all we do is we set this equal to 2P. So we have 2P equals P times 1 plus R over 4, since it's compounded quarterly, and that's raised to the 4, which is our compounded quarterly, times 6 power because we have 6 years. So, whoops, I skipped ahead a little bit there. If we divide both sides by P, what's going to happen is our P is going to go away, so we're just left with 2 equals 1 plus R over 4 raised to the 24th power. Now, this is not particularly nice, but in order to get rid of this kind of nasty power of 24, we need to take a root. So in this case, we'll take the 24th root of both sides. It's just going to go away on the right-hand side. And on the left-hand side, you have the 24th root of 2 equals 1 plus R over 4. So if you solve for R, what you're going to do is you're going to subtract 1 first. So you have 24th root of 2 minus 1 equals R over 4. And then in order to get rid of that denominator, we need to multiply both sides by 4. So what we end up with is R equals 4 times the 24th root of 2 minus 1. If you're having trouble plugging in the 24th root in your calculator, it kind of depends on what calculator you have. What you can do is you can raise 2 to the 1 over 24th power. So remember, if you have the square root, you can raise that to the 1/2 power. If you have cube root, that's the same as raising to the 1/3 power. So if we have the 24th root, you can just raise to the 1 over 24 power. So in this case, we get 0.1172 approximately, which is going to be about 11.72%. So it says that we need an annual interest rate of 11.72% in order for us to be able to double our principal in 6 years. Okay, how long will it take to double an investment if it earns 6% compounded continuously? And then how long would it take to triple at this rate? So since it's compounded continuously, we're going to be using this formula down here, A equals P times E to the RT. And again, we just plug in 2P for our future value because we want it to be 2 times our principal. Divide by P, so we get 2 equals E to the 2 equals E to the 0.06t power. And now you'll see why we waited until after logarithms in order to solve this, because before we had done logarithms, we wouldn't be able to do this. But now what we can do is we can remember what we did about e's and getting rid of exponents that had variables in them. So we take natural log of both sides. So we have ln of 2 equals ln of e to the 0.06t. Now if you recall, ln of e to any power is just going to be that power. So we get ln of 2 equals 0.06t. And then we divide by 0.06, so we get t equals ln of 2 over 0.06, which if you do this in your calculator, you should get about 11.55 years. Now, if we want to triple it, instead of plugging 2p in for our future amount, we plug 3p in, and we solve it the same way. So we divide by p, so we get 3 equals e to the 0.06t. Take natural log. Again, if you have ln of e to any power, it's just going to be that power. And then we divide by 0.06, so we get t equals ln of 3 over 0.06, which is going to be 18.31 years. Now, it does make sense that it's going to take quite a bit longer to triple your money versus just doubling. Okay, so now we're going to move on to section 6.8, which talks about exponential growth and decay, Newton's law, and logistic growth and decay. So the first thing we want to do is find equations of populations that obey the law of uninhibited growth. So we have a couple of pictures here that kind of show it. A of t is going to be equal to a naught times e to the kt power. Now we have something that's increasing when k is greater than 0, and we have something that's decreasing when k is less than 0. A0 or a sub 0 is just our initial amount. Okay. This one, though, is increasing. This one is decreasing. So a model that gives the number of cells in a culture after a time t has passed is going to be given by the equation down here. N of t equals n sub 0 e to the kt, where n0 or n naught is the initial number of cells. K is a positive constant that represents the growth rate. And in this case, since we're talking about growth, we're going to have something where we have k, or our growth rate, is going to be greater than 0. We would have a decay rate if it were less than 0. So let's do an example that we have here. A colony of bacteria grows according to the law of uninhibited growth according to the function n of t equals 90 times e to the 0.05t, where n is measured in grams and t is measured in days. So first thing we want to do is determine the initial amount of bacteria. Now, we know that initial amount is going to be when no time at all has passed. So what we do is we just substitute t equals 0. And if we do that, we should know that anything to the 0 power is just going to be 1. 1 times 90 is just going to give you 90. The other thing to note is that the initial amount is always going to be this number in front of your e. So we know that we start with 90 cells. If we want to figure out the growth rate, all we do is we look at the number that's in the exponent and in front of your t. So it should be k equals 0.05, which we know is 5%. If we want to know what the population is after 5 days, that means that we need to substitute 5 in for t. So n of 5, that's going to be what we want, is going to be equal to 90 times e to the 0.05 times 5 power. You need to make sure that you evaluate this exponent before you raise e to it. And if you do that, you should get 116 cells left after 5 days. The next question asks us how long it's going to take for the population to reach 140 cells. So this is a little bit different than what's given in C. C wanted you to find the population after 5 days. In this one, they give you the population and they want you to tell them how long it takes to reach that population. So what we're going to do is we're going to take our 140, which is what we're interested in, and we're going to substitute that in for n of t. So we have 140 equals 90 times e to the 0.05 t power. Now, before we solve anything like this, we need to get e by itself. So we're going to divide both sides by 90. So we get 140 over 90 equals e to the 0.05 t. Now, again, if you have a variable in your exponent, we're going to have to take natural log or log to get rid of that. Since we have an e, we're going to want to take natural log. So we take ln of both sides. You'll see they also reduce 140 over 90 to 14 over 9. So we have natural log of 14/9 equals 0.05 t. If you recall from the last problem, ln of e to any power is just the power. And then we divide by 0.05. Sorry, this little thing is in the way down here, but we have ln of 14/9 over 0.05. This would be your exact answer, but when we're talking about problems like this, we probably want to know an approximate answer because it makes a little more sense. And if we do that, we get 8.8, and that's going to be in days. So it takes 8.8 days in order for our population to reach 140 cells. Now, if we want to know how long it takes to double, if you think about it, we know that our initial amount is 90, so double that would be 180. So we just set 180 equal to our n of t, and then we divide. And you'll notice 180 divided by 90 is 2, okay? This is not a coincidence. Anytime we're doing doubling time or tripling time, it's always going to end up with that number on your left-hand side. So in this case, we have 2 because it's doubling time. And then we take natural log of both sides. So we have natural log of 2 equals 0.05t. Remember that exponent when you have ln of e to some power, that's all you're left with. And then we divide by 0.05. So our exact answer is ln of 2 over 0.05. Our approximate answer would be about 13.9 days. That's how long it would take our population to double from 90 to 180. Okay, a colony of bacteria increases according to the law of uninhibited growth. If n is the number of cells and t is the time expressed in hours, express n as a function of t. And then we want to say if the number of bacteria doubles in 2 hours, find the function that gives the number of cells in a culture. So we know we're going to have this kind of initial equation. This is always what it's going to look like at first. And then the next thing we're told is that the bacteria doubles in 2 hours. So we know that after 2 hours, which is going to be t equals 2, we end up with twice the number that we started with, so 2 times n naught. And if we go ahead and solve this, if we divide both sides by n naught, we get 2 equals e to the 2k power. We take natural log of both sides, so you're just left with ln of 2 equals 2k, and then divide by 2. So we get a growth rate, or k, of ln 2 over 2, which is going to be 0.3465. So if we want to write the function, we say that n of t is equal to n naught times e to the 0.3465 736 times t power. So if we want to know how long it's going to take our colony to triple, we just set n of t equal to 3 times our original amount, which is our n naught, divide by n naught, take natural log of both sides, and we get an exact answer of ln of 3 over 0.3465736, which was our growth rate, and that's going to be about 3.2 hours. If we want to know how long it's going to double a second time, to double a second time, we know that if a population doubles in 2 hours, it's going to double again in a total of 4 hours. So that doesn't change. Okay, now we want to look at some equations that obey the law of decay. So this looks very similar to uninhibited growth, except most of the time here we're going to be talking about radioactive material, and in this case k is going to be less than 0, so it's going to be negative. A naught is the original amount, k is the negative number that represents your rate of decay. So you'll know if you have a decay problem if your rate is negative. If your rate's positive, then you have a growth problem. So traces of burned wood, along with ancient stone tools in an archaeological dig in Chile, were found to contain approximately 1.67% of the original amount of carbon-14. If the half-life of carbon-14 is 5,600 years, we want to approximate when the tree cut and burned, or when the tree was cut and burned. So we're going to use our uninhibited decay, and what we want is we want half-life in this case. So instead of doubling time or tripling time, you're going to see stuff like half-life. So we want half of our substance, or half of A naught, to be left. So in order to do that, the other thing is we plug in our 5,600 for t, because we know we have 5,600 years. Divide by A naught, so we're left with 1/2 equals e to the 5,600k power. Take natural log. And then divide, we have ln of 1/2 over 5,600, that's our exact amount, which gives us an approximate amount of negative 0.000124. So now we want to know if the half-life of carbon is 5,600 years, approximately when was the tree cut and burned. So if we know that 1.67% is left, that's what we're going to set in front of our A naught. So if we want 1.67% of our original amount, we're going to do 0.0167 times A naught equals A naught times E to the same rate, which is our decay rate, times T power. So this time we don't know what T is. So we divide by A naught, take natural log, and we end up with ln of 0.0167 divided by negative 0.000124, which gives us 33,003 years. All right, now we want to use Newton's law of cooling. So the temperature U of a heated object at a given time t can be modeled by the following function. U of t is equal to t, which is our capital T, t plus U naught minus t times e to the kt power, where k is less than 0. Our capital T is going to be our constant temperature, and that's surrounding the medium. U naught is going to be the initial temperature of the heated object, and K is going to be a negative constant. So let's say that a cake is heated to 350 degrees Fahrenheit and is then allowed to cool in a room whose air temperature is 70 degrees Fahrenheit. If the temperature of the cake is 300 degrees Fahrenheit after 5 minutes, when will its temperature be 200? So what we want to do is we use our equation. So we have U of t equals 70, which is our room temperature, plus our initial temperature, which is 350 minus 70, multiplied by e to the kt power. And what we do is we use the fact that U of 5 equals 300. So we know after 5 minutes that it's at 300 degrees. So we set 300 equal to our U of t, and that's going to be 70 plus 350 minus 70 times e to the k times 5 power, because we have 5 minutes. And we go ahead and simplify some of this stuff. 300 equals 70 plus 280 e to the 5k. Subtract 70 and divide by 280. So we're left with 230 over 280 equals e to the 5k. Take natural log of both sides since we have a variable in our exponent. So we have natural log of 230 over 280 equals 5k. That reduces to 23 over 28, and then we divide by 5, or multiply by 1/5 as they've done here, and we get negative 0.039342. So that gives us our k. And then what we want to know is how long will it take, let's see, to be 200 degrees Fahrenheit. So what we do is we set 200 equal to our U of t, and then we're going to solve for t. We have our rate that we just found. Subtract 70, divide by 280, take natural log, and if we solve this, we get about 19.5 minutes, which seems reasonable if you think about a cake cooling. It's decreased by 50 degrees in 5 minutes, and it takes a total of about 20 minutes to decrease by another 100 degrees. Okay, it says determine the elapsed time before the temperature is 100 degrees Fahrenheit. So this one's really similar. Instead of 200, though, we have 100. So we have 100 equals 70 plus 280 times e to the negative 0.039342 t power. So we subtract 70 and divide by 280. So we get 30 over 280 equals e to that same power times t. Take natural log and divide by that same number, and we get 56.8 minutes. So question C asks us, what do we notice about the temperature as time passes? So if we look at our function, you can see that t increases exponentially as this part right here approaches 0. So the temperature of the cake approaches the room temperature of 70 degrees Fahrenheit. Okay, using logistic models. So in a logistic model, the population P after a time t is given by the following function. We have P of t equals C over the whole quantity 1 plus A times e to the negative bt power. A, B, and C are going to be constants. A is greater than 0, as is C. The model is a growth model if B is greater than 0, and the model is a decay model if B is less than 0. So we have something here where it's a growth model and then a decay model. Some properties of the logistic growth function. The domain is always going to be all real numbers. The range is going to be from 0 to C, where C is the carrying capacity. There aren't any x-intercepts, but the y-intercept is going to be P0. There are two horizontal asymptotes. One is going to be at y equals 0, and the other is at y equals C. It's going to be increasing if B is greater than 0, which is the first, this graph right here on the left, and decreasing if B is less than 0. There's going to be an inflection point, so that's where it changes from concave up to concave down, or the other way around, where P of t equals 1/2 of the carrying capacity. The inflection point is the point on the graph where you kind of see this change here. So if you look, this looks like it's kind of going upwards, all right? And then if we look here, we have something that's more concave down. So the graph is also smooth and continuous, and it doesn't have any corners or gaps. Okay, so we have a wood product here. It classifies wood products according to their lifespan. So there are 4 classifications: short, which would be 1 year; medium short, which is 4 years; medium long, which is 16 years; and long, which is 50 years. Based on data obtained from the European Forest Institute, the percentage of remaining wood products after T years for wood products with long lifespans, such as those used in a building industry where you would want something that has a long lifespan, is given by the following function. All right, if we want to know the decay rate, all we do is we look at the number that's next to T, and we can see that our decay rate is going to be 5.81%. The percentage of remaining wood products after 10 years, all we have to do is we just have to plug 10 in for T. So we're finding P of 10. So this really just requires that you're very careful in putting it in your calculator. If you want to do it all at once in your calculator, make sure you put parentheses around your entire denominator. So you get 95 as your answer. So that means that 95% remains after 10 years. How long does it take for the percentage of remaining wood products to reach 50%? So instead of being given a time T, what we're given is P of T. So we're given 50, so we substitute that in. And then we multiply by our denominator in order to get rid of it. And then we go ahead and, let's see, it looks like we divide by 50 and subtract 1, divide by 0.0316, and we're left with this right here. E to the 0.0581t equals 31.8956. This looks just like all of the other problems we've solved today. We take natural log of both sides, and we go ahead and divide to solve. So we get 59.6 years. So it's going to take about 60 years for the percentage of remaining wood products to reach about 50%. And then it asks us to explain why the numerator in the model is reasonable. And if you think about it, 100.3952 seems pretty reasonable because the maximum percentage of wood products remaining is going to be 100%. So if we set T equal to 0, that's what would happen there. Okay. Now I just want to go through a couple of things from Chapter 6 that we've already gone through in previous lectures, just a couple of extra examples since you do have a quiz over Chapter 6 material this week. Okay, so let's say we have a function f of x equals 2x plus 1 over x minus 1. They do tell us that x cannot equal 1, and the reason for that is because if you plug 1 in, you get a 0 in your denominator, which is obviously not what we want. This is a one-to-one function, so we want to go ahead and find its inverse and then check the result. So if you recall, in order to find the inverse, you interchange the variables x and y. So everywhere you see a y, you put an x. Everywhere you see an x, you put a y. So we end up with x equals 2y plus 1 over y minus 1. And then we go ahead and solve for y. So whenever we have a fraction here where we have y in our denominator, we need to multiply by that denominator first. So we have x times y minus 1 equals 2y plus 1. Distribute. So we have xy minus x equals 2y plus 1. Get everything with a y on one side of our equation and move everything else to the other side. So in this case, we subtract 2y from both sides and add x to both sides. So we're taking our negative x and we're moving it over here. And we're taking our 2y and we're moving it on our left side. So we have xy minus 2y equals x plus 1. And then we can factor out a y. So we have y times the quantity x minus 2 equals x plus 1. And then we divide by x minus 2. So we're left with y equals x plus 1 over x minus 2. And we always want to write that, instead of writing it as y equals, we write it as f inverse of x equals x plus 1 over x minus 2. And then one thing you should note about this is that x is not equal to 2, because if x is 2, then it makes your denominator 0. All right, I'm going to skip the check for this one because I think it's pretty complicated, but all you have to do is take your inverse and plug it into your original, take your original and plug it into your inverse, and make sure that each time you get x. Okay, now I want to solve a couple of exponential equations. So let's say we have 2 to the power 3x minus 1 equals 32. So anytime you have the ability to get the same base, you want to go ahead and do that. Once you have the same bases, then you can essentially just ignore the base and keep the exponents. So we know that 32 is 2 to the 5th power. So we're left with 2 to the 3x minus 1 power equals 2 to the 5th. And then we just set our exponents equal to each other. So we have 3x minus 1 equals 5. So we get x equals 2. All right, this one over here. We have a lot of e's, a lot of kind of crazy stuff going on, but what we really need to do is we just need to make this right-hand side look nicer. So if you recall, when you have a power to a power, that's just multiplying. So really this is just e to the negative 4x over e to the 3x. And then if you remember, when you're dividing and you have the same base and different exponents, you can subtract the exponents. So if we take negative 4x minus 3x, we get negative 7x. So what we have is e to the 2x minus 1 equals e to the negative 7x. Since they're the same bases, even though they're e, it doesn't matter. Since they're the same, we can just set the exponents equal to each other. So we have 2x minus 1 equals negative 7x. So we get x equals 1/9. Okay, we can also solve logarithmic equations. So if we have log base 3 of 4 equals 2 times log base 3 of x, what we want to do is go ahead and write anything that's out front as a power. So we have log base 3 of 4 equals log base 3 of x squared. And now that we have the same log bases, we can basically just ignore that part. So we're left with 4 equals x squared. We take square roots and we get plus or minus 2. One thing to remember is that the domain of logarithmic functions is positive numbers, so we have to check for extraneous. So if we take negative 2 when we plug it in here, we would have log base 3 of negative 2. We cannot do that, so that one doesn't work. All right, we have another one here. Log base 2 of x plus 2 plus log base 2 of 1 minus x equals 1. We want to combine this so that we just have one logarithm. So if you recall, when we add, we can change that back into multiplication as long as we have the same bases, which we do. So we have log base 2 of x plus 2 times 1 minus x equals 1. And then we rewrite this so that it's in exponential form instead of logarithmic. So we have 2, that was our base, to the first power equals x plus 2 times 1 minus x. We go ahead and FOIL that out. So we have 2 equals negative x squared minus x plus 2. Subtract 2 from both sides, we get x squared plus x equals 0. So if we solve, we get x equals 0 or x equals negative 1. Both solutions are in the domain, so they both work. All right, let's do another. Let's say we have 3 to the x equals 7. Now we've done a lot like this today, so you should be comfortable with this by now. But anytime you have a variable in your exponent and you're not sure how to solve, what you want to do is you want to get whatever piece this is by itself and then take natural log of both sides. So we have ln of 3 to the x equals ln of 7. And then we bring our exponent out front. So we take x ln 3 equals ln 7 and then divide. So the exact answer is just ln 7 over ln of 3. Which is about 1.771. Now there's nothing wrong with using a different base for your logarithm as well. You could just use log, which would be a base 10. You'll get the exact same answer. All right, this one looks very similar. We have 5 times 2 to the x equals 3, except with this one you have this extra 5 times. So anytime you're doing this, you always want to make sure you get this exponent by itself first. Or not the exponent, the part that's attached to the exponent. So we divide by 5 first, so we have 2 to the x equals 3/5, and then we take natural log of both sides.